Welcome to this mini tutorial on artificial intelligence or AI applied to control systems. In this mini course, I will first give you an intuition on how backpropagation works in neural networks. I will then show you how Q-learning works in the context of optimal pathfinding process in a simple grid world. We will have a starting and an ending point, and then an algorithm will use reinforcement learning to learn which the optimal path is from start to finish. Finally, I will introduce you to a state-of-the-art machine learning actor-critic algorithm, twin-delayed DTPG or TD3, and we're going to apply it to a vehicle suspension system of a half-car model in order to tune the two PID controllers using that AI technique in PyTorch. This tutorial will have theory and code implementation. The theory is explained here on YouTube. However, the relevant Python files and the videos that explain the code are offered in my free Udemy tutorial called Vehicle Suspension Control 4 PID Tuning with AI TD3. The link's in the description. Go ahead and enroll in the course. It's completely free and you will gain access to the code files and their explanations. Also note that the free coupons that I offer for that, they have limitations in terms of time and the number of enrollments. However, don't worry, I will be renewing them periodically. But okay, let's start with backpropagation. I will give you an intuition on how it works in principle using this simple, fully connected neural network. In here, every circle represents a neuron. And just like neurons in your brain are connected in many different ways, so are the artificial neurons in neural network algorithms. You can see that these neurons are ordered in layers. You have input and output layers and also hidden layers in the middle. You can have many hidden layers, but we will only have one to keep it simple. In addition, we also have special neurons called bias neurons that are connected to the hidden and output layers. The values of the bias neurons are 1. Every connection between neurons comes with a number that we either call weights if that connection is between regular neurons and we denote them with WI, or biases if the connection is between a bias and some other regular neuron and we denote them with BI. These weights and biases determine the strength of a connection between two neurons. For instance, if W1 equals 0, then that would essentially mean that there is no connection between these two neurons here. In fact, let's give them names. Let these two be I1 and I2, let these two be H1 and H2, and let these two be O1 and O2. Alright, that's all wonderful, but what do we even need this structure for? What are we trying to achieve here? Let's give the input neurons some values. Let them be 0.1 and 0.2. These are the values that we insert at the entrance of the neural net. And when we do so, the network will pass these values through it. As they propagate through the network, in this forward direction, they will somehow be modified, and then the network will output some values at the exit. In other words, O1 and O2 will have some values, and these outputs will depend on the weights and biases in the network. Once we have given the network the inputs I1 and I2, we can very easily find the outputs O1 and O2 using linear algebra. H1 can be written like this, and H2 will be this one. You multiply the relevant weights by the values that are assigned to input neurons, and then you multiply the relevant biases by the values in the bias neurons. You add everything up, and you can formulate it in a matrix vector form in this way. And then once you have the values for H1 and H2, I can use them to calculate O1 and O2 by using the weights and biases here. I can reformulate it in this way, and so you can clearly see that the outputs depend on the weights and the biases. By the way, currently I'm leaving something very important out from this network. There is no activation function here. We will talk about it soon. I want to avoid it first in order to highlight the issues you would face if you didn't have activation functions in neural networks. But suppose that I want to enforce the output neurons to have certain values. Let's say that when I insert these values for the inputs, I want the outputs to have these values. I want them to be enforced. I want them to be guaranteed. The only way I can make that happen is when I find the right values for the weights and biases that will map these input values to the desired or required output values. Since we don't know in advance what these required weights and biases are, we would first initiate them with some values. Let's say all W's will be 0.2 and let all B's be 0.3, and then we will use some kind of iterative numerical algorithm to iteratively change them so that they would converge to the required values of weights and biases that would correctly, or at least approximately, map these inputs to the desired outputs. And this process is learning. That's when your network is learning. Or we can also say that we are training the network. Training means trying to get these weights and biases closer and closer to the optimal ones. By the way, the desired outputs that you want to have, they're also called target outputs or target values. Also, let this be our H vector. I will call this matrix like this, W sub H. Let this one be the I vector. Let this one be the BH vector. Then this will be the O vector. This is the WO matrix. This is again the H vector. And this is the BO vector. However, as mentioned before, currently this network is not complete. The form that we have here can only produce very limited target values in very limited cases. Let's see what is missing in the next video. Thank you.